Uploads. Imagine walking through a new neighborhood where most homes are barely more than wooden frames.
You expect unfinished structures and the early stages of construction everywhere.
But suddenly you see a fully finished mansion standing impossibly complete.
That strange surprise mirrors what astronomers feel when viewing Webb's discoveries.
Webb lets us peer into the most distant regions of the cosmos. Looking that far means looking back to the universe's earliest moments.
We expect a young, messy cosmos, filled with scattered gas and infant stars.
Instead, Webb reveals galaxies that look shockingly mature for their age.
Even veteran scientists double-check the data to believe what they see.
These galaxies appear only a few 100 million years after the Big Bang.
Imagine a 2-hour universe film ending at minute 3.
By all logic, these galaxies should not be so big or organized yet.
Cosmology predicts the early universe needed far more time to cool and form stars.
Yet here we see galaxies as large as the Milky Way, shining brightly.
So naturally, we must ask how this is happening so quickly.
One idea is that dark matter collapsed earlier than expected.
Dark matter may have acted like a cosmic accelerator for early star formation.
Another explanation is gravitational lensing, magnifying distant galaxies.
Lensing can trick us into thinking something is older or larger than it truly is.
But some believe the early universe simply behaved differently.
It may have cooled faster or formed stars with surprising efficiency.
Structures may have emerged through processes we have yet to identify.
After decades in astrophysics, these puzzles still amaze me.
Webb isn't just giving us clearer pictures, it's bending our cosmic timeline.
These early giants suggest the universe grew in leaps, not slow steps.
So what else might be hiding deeper in cosmic time? Have we underestimated how quickly the universe organizes itself? Or have we overlooked entire chapters of how galaxies truly form?
These observations force us to question long-held assumptions.
The universe may not follow our comfortable, predictable timelines.
Webb's images reveal glimpses of a universe we never modeled. Every deep field image presents something unexpected.
Early galaxies defy nearly every prediction we have made.
It feels like the universe had a head start we never accounted for.
If galaxies formed too soon, what does that mean for our models?
Perhaps dark matter shaped the early cosmos with greater influence.
Or extreme early conditions triggered rapid collapse of gas clouds.
These clues challenge physics as we currently understand it.
These galaxies may hold the key to rewriting cosmic history.
They remind us how little we truly know about early cosmic evolution.
Every Webb observation deepens the mystery. And each discovery raises more questions than answers. Questions like these are what push science forward.
These early galaxies are windows into the universal's beginnings.
They tell a story of rapid, unexpected growth.
They show a universe acting as a fast-moving engine of creation.
Looking deeper means preparing to update our theories. The universe evolves faster and more dramatically than we imagined.
Webb shows us a cosmos that wastes no time. Something pushed early galaxies to grow at extraordinary speed.
Whether dark matter, physics, or timing, we must uncover the cause.
These discoveries push us to test the limits of our knowledge. They remind us that scientific understanding is always temporary.
If galaxies formed this quickly, what formed even faster?
Webb hints cosmic evolution may be far more dramatic.
This is not a calm universe. It is a universe in overdrive.
Every deep field view carries us further into the unknown.
Each step challenges the timeline we've trusted for years.
If the timeline is wrong, our story of the cosmos must be rewritten.
That possibility is as thrilling as it is humbling.
Webb has only just begun its journey.
And the universe is just starting to reveal what lies beyond.
Imagine an airport where each gate seems to follow a different rhythm of time.
One gate moves calmly, while another rushes forward.
Now stretch that uneven rhythm across the entire universe.
Webb hints that time itself flowed differently in early space.
Some regions aged quickly, while others lagged behind.
This challenges our belief that time is uniform everywhere.
These shifts may explain structures forming earlier than expected.
Imagine the early universe as a landscape shaped by time.
Scientists wonder if ancient galaxies lived under different clocks.
Let's slow down and explore what this means.
Time is influenced by speed and gravity, as relativity shows.
Even GPS satellites adjust their clocks to stay accurate.
Now imagine applying such corrections to the early universe. Early space was uneven, filled with dense and empty regions.
Gravity may have slowed time in dense zones. Meanwhile, lighter regions allowed time to move faster. These offsets could make galaxies look impossibly early.
Think of two runners starting together, but facing different terrain.
One runs on pavement, while the other struggles in deep sand. They share a start time, but finish far apart.
The early universe may have behaved in exactly that way.
Some theories suggest early expansion varied by region.
Faster expansion could stretch or compress ancient light. Webb detects clues hidden in that distorted ancient light.
These signals make galaxies appear off schedule.
We may be misreading the true ages of ancient structures. Or we may be missing key physics from the universe's youth.
Imagine a film made with cameras at different frame rates.
Webb may be seeing the universe's version of that mismatch.
Time may have flowed differently across early space.
If true, we must rethink our entire cosmic timeline.
They may have evolved under accelerated clocks.
Or some regions slowed dramatically under heavy gravity.
Early cosmic history may be far more chaotic than imagined.
Some galaxies grew rapidly under extreme conditions.
Others evolved slowly in gravitational pockets.
These differences reshape our view of cosmic evolution.
Webb reveals a universe built on uneven rhythms.
It shows us a cosmos far stranger than expected.
Every deep field observation introduces new puzzles.
Some galaxies seem too advanced for their apparent age. Time offsets might explain those impossible structures. We may be missing early chapters of the universe's story. And those chapters may change everything we know.
After decades in astrophysics, mysteries like this still humble me.
Webb keeps reminding us how little we truly understand. Time may be the most misunderstood force in the cosmos. And Webb is helping us uncover how it behaved long ago.
Whatever the explanation, new discoveries await us deeper in time.
And the universe is only beginning to reveal its hidden rhythms.
Imagine opening the universe's diary and finding a fully formed quasar in its first pages.
These ancient quasars force us to rethink how quickly giants can arise.
They appear only a few 100 million years after the Big Bang.
Their supermassive black holes are far larger than models allow so early.
It's like meeting an adult female athlete inside a kindergarten classroom.
They shine because infalling matter heats to extreme temperatures as it falls.
A quasar's brightness can outshine its entire host galaxy.
To create one, the central black hole must already be enormous and active.
Traditional models expect black holes to grow slowly over long timescales.
Some theories propose direct collapse of massive gas clouds into seeds.
Huge primordial clouds might have collapsed directly into black holes.
Those seeds could begin orders of magnitude heavier than single-star remnants. Starting larger makes it easier to reach supermassive scales quickly.
Another idea invokes extremely rapid, super Eddington accretion episodes.
In the dense early universe, black holes may have fed at astonishing rates.
Such hyperaccretion could break the limits assumed in modern models.
Gravitational lensing can magnify distant quasars and complicate estimates.
But lensing cannot account for every massive early quasar we observe.
Webb keeps revealing more of these ancient bright beacons.
Each detection forces us to redraw the early cosmic timeline. They show the universal's youth was not slow or tame.
Instead, it was dense, chaotic, and remarkably productive. These quasars act as cosmic lighthouses from deep time.
Their light has traversed almost the entire universe to reach us.
They map the first large-scale structures that formed after the Big Bang.
Some host galaxies already carried enormous mass at surprising ages.
This raises fundamental questions about galaxy formation physics.
Did galaxies build black holes? Or did black holes shape galaxies first?
Perhaps black holes sculpted their surroundings from the very start.
Webb's discoveries point to a more dramatic cosmic dawn than expected.
A period filled with rapid starbursts, dense flows, and violent dynamics.
Primordial matter might have clumped faster and more efficiently than thought.
These quasars illuminate that turbulent, energetic environment. They serve as fossils, recording conditions in the universe's infancy.
Their output sculpts and heats the space around them on vast scales.
Jets and winds from quasars can regulate star formation in host galaxies.
These feedback processes influence early galaxy evolution significantly.
Some quasars appear far brighter and more massive than any prior predictions.
They push astrophysics into unexplored theoretical territory. The universe may have grown structures, not by slow steps, but by leaps. Certain regions likely experienced explosive growth rather than steady accretion.
These discoveries hint at missing physics in our standard simulations.
Perhaps cooling was far more efficient, or dynamics more violent early on.
Dark matter might have played a larger, active role in early collapse.
Dense dark matter halos could accelerate gas accumulation and collapse. Such halos might explain unusually rapid black hole formation. Some quasars challenge assumptions about uniform cosmic expansion effects. Their light reveals unexpected patterns in the distribution of early matter. Webb captures details that older telescopes could not resolve clearly.
Its infrared vision penetrates dust and reveals faint ancient structures.
Ancient quasars appear with stunning clarity in Webb's images.
Spectra show chemical fingerprints tracing early generations of stars.
Those stars likely formed rapidly around the growing black hole.
The quasar environments were intense, short-lived, and transformative.
The early universe appears to have moved at a breathtaking pace.
Quasars suggest that pace was almost frantic in some regions.
Understanding them will require rewriting parts of cosmic history.
They break the neat timelines of conventional hierarchical models.
They show nature often defies our simplified theoretical rules. Each new quasar reshapes our narrative of early black hole growth.
They force us to reconsider how quickly galaxies assemble structure.
They remind us how little we truly know about cosmic dawn. Even after decades, these discoveries still surprise working scientists.
They reveal a universe full of ambition, chaos, and rapid construction.
A cosmos that built giants from its earliest moments. And Webb is only at the beginning of its deep survey mission. Countless quasars may yet lurk in the unobserved darkness. Their stories are written in ancient photons crossing cosmic time.
We're just beginning to decode what those photons mean for history.
The universe is far more mysterious and inventive than expected.
These quasars invite us deeper into that astonishing mystery.
Whatever the eventual explanation, New insights are coming.
Because the early universe still has many secrets left to share.
And Webb is helping us uncover them, one by one. Imagine holding a tiny stone that feels impossibly heavy for its size. That strange weight mirrors how red nuggets defy our expectations.
These galaxies are shockingly small, yet incredibly massive.
Webb is uncovering more of them than anyone predicted. Red nuggets contain the mass of hundreds of billions of suns.
Yet they fit inside a space far smaller than the Milky Way's core. Imagine a small town holding the population of New York City.
That's the level of stellar crowding inside a red nugget.
These compact giants formed early, when the universe was still chaotic.
Picture a teenage universe growing faster than anyone expected. Red nuggets seem like relics left from that intense period. Their reddish glow comes from dense, aging stars and stretched light. Webb sees them clearly in the distant infrared.
But the real surprise is how early they appear.
Some existed just 1 or 2 billion years after the Big Bang.
They reached enormous mass long before our models allow.
It's like seeing an Olympic champion in a kindergarten classroom.
Something about the growth timeline simply doesn't add up. One idea says they formed stars at explosive speed.
Billions of stars may have formed in a short, intense burst.
Another theory sees them as the early cores of today's giant galaxies.
Over time, larger galaxies could swallow them and grow around them. Some massive galaxies may still hide red nuggets at their centers. But another possibility is far more provocative.
Maybe our models never captured how the early universe truly behaved. Matter might have clumped faster and more efficiently than expected.
Early cosmic conditions may have favored extreme compact growth.
These galaxies could represent a phase we never modeled correctly. What makes this more striking is how many Webb is finding. They aren't rare. They're abundant in the early universe.
That forces us to rethink how galaxies assembled their mass.
Star formation may have been far more intense than we assumed.
Even the physics of early gravity may need reconsideration. Red nuggets challenge nearly every timeline we built.
They suggest galaxies didn't always grow slowly and steadily. Instead, some grew explosively fast under extreme conditions.
Their density is unlike almost anything in today's universe.
Imagine stars packed 1,000 times tighter than in our neighborhood.
Walking through one would feel like stepping into cosmic downtown. Their existence hints at powerful early processes now gone. They may hold clues to how massive galaxies formed their hearts. Webb lets us witness these long-lost building blocks directly. And each discovery deepens the mystery further.
Why did the early universe create so many of these dense objects?
What conditions allowed such extreme star packing?
And why do so few exist in the universe today?
Perhaps many were swallowed by larger galaxies over billions of years.
Or maybe they represent a brief but intense evolutionary phase.
Whatever the cause, they rewrite how we think galaxies begin. They force us to revisit the universe's earliest growth spurt.
After decades in astrophysics, I still find moments like this humbling. Webb keeps reminding us that the cosmos is stranger than our theories.
Red nuggets shine like ancient warnings we almost missed.
They tell us the early universe was anything but slow or gentle.
Instead, it was fierce, crowded, and astonishingly productive. These compact giants challenge everything we thought we understood. And they open the door to deeper, more profound questions.
Because if the early universe built these so quickly,
what else is still hiding in the darkness of deep time?
imagine looking at a city map at night and seeing patches of pure darkness.
Those dark spots seem empty, yet you sense hidden structures beneath.
The universe has similar dark regions that appear completely void.
But Webb reveals these places are not empty at all.
Subtle bends in light suggest something massive is hiding there.
These signs point toward a vast network of dark matter.
Dark matter forms an invisible framework holding the universe together. To understand this mystery, we must ask a simple question.
What keeps galaxies from flying apart as they spin?
Visible matter alone doesn't create enough gravity to hold them.
Something unseen must provide the extra binding force. That hidden something is what we call dark matter. It doesn't shine, reflect, or absorb light. but its gravitational pull is unmistakably real.
Webb details tiny distortions that reveal this hidden structure.
These distortions occur even in regions we thought were empty.
It means dark matter fills the cosmic gaps like unseen glue.
Picture the universe as soap bubbles in a dark room.
The bubbles are galaxies, and the walls are dark matter filaments.
These filaments act like scaffolding inside a skyscraper.
You rarely see the beams, yet the building depends on them. Webb's observations show these dark regions are anything but still. Light bends slightly as it travels through the invisible mass. This bending is called weak gravitational lensing.
Weak lensing is subtle, but incredibly revealing.
Think of watching an outdoor concert at night.
You can't see the performer in shadow.
You know someone is there from the effect, not the sight.
That's exactly how we detect dark matter in space.
Webb reveals dark matter stretching across cosmic highways. Galaxies gather and drift along these invisible pathways.
This structure forms what cosmologists call the cosmic web.
Webb shows the web is more intricate than simulations predicted. Some places appear as dense knots packed with dark matter.
Others form thin threads, stretching across vast emptiness.
Together, these threads shape the universe's architecture. This framework guides how galaxies form and evolve.
Dense nodes may trigger rapid star formation early on.
Thin strands shepherd smaller galaxies through space.
Understanding this web reveals how the universe began.
It raises a deep question about cosmic structure.
If dark matter forms the framework, what shapes the framework? Early conditions may have differed from our expectations. Galaxies may have formed sooner than our models predict. Webb uncovers the earliest layers of this hidden skeleton.
Even today, dark matter guides the motion of galaxies. The universe expands across this unseen stage. These discoveries remind me how mysterious the cosmos remains.
Much of the universe still lies hidden beyond our sight. Dark matter may be the cosmos's most misunderstood element. It shapes a gravitational landscape we're only beginning to map. Webb helps reveal these invisible contours.
Each lensing signal uncovers more of the cosmic skeleton.
Even empty space is filled with unseen structure. These discoveries reshape our understanding of cosmic evolution.
The underlying framework is richer than we imagined.
Dark matter is the silent architect of the universe. Its design grows more complex with every observation. We are only beginning to chart this invisible world.
Webb lets us explore deeper than ever before. With each image, hidden structures emerge from the dark.
These dark regions hold clues to the universe's earliest forms.
They may explain why galaxies grew quickly at cosmic dawn.
They may reveal why some regions flourished while others stayed empty.
Answers lie within shadows once thought empty. Each discovery brings us closer to understanding the unseen. Even the emptiest places contain extraordinary secrets. And we have only begun to explore what lies in the dark.
Imagine walking into a daycare expecting calm, only to see dozens of children arriving at once.
That overwhelming surprise mirrors what Webb is seeing in distant galaxies.
Some early galaxies are creating stars at astonishing, almost impossible rates.
The Milky Way forms just 1 or 2 stars per year.
But these galaxies are forming dozens, even hundreds, every single year.
And they did this when the universe was still very young.
That speed breaks nearly every model we've used to describe star formation.
Star birth isn't instant. It needs gas, collapse, and intense pressure.
Yet these galaxies behave like factories, running beyond physical limits. One idea is that early galaxies held far denser gas than today. Dense fuel means faster collapse and far more opportunities to form stars.
It's like trying to light a fire using an entire forest of dry wood.
Another idea is that many early galaxies collided frequently.
Galactic mergers compress gas violently, triggering massive starbursts.
Webb sees twisted shapes and long streams pointing to past collisions. But even mergers can't fully explain these extreme star creation speeds.
Some galaxies seem to burn through their fuel in a cosmic sprint.
It raises a bold question. Did the early universe allow new physics? Or are we seeing a kind of star formation no longer possible today?
Picture a forest after a powerful storm opens the canopy. Sunlight pierces a torn treetop, illuminating fast-growing saplings below.
Suddenly, every seed has the perfect conditions to grow at once.
The young universe may have experienced similar bursts of opportunity.
But rapid star formation comes with dramatic consequences. Too many young stars can blast away the remaining gas.
The galaxy shines brilliantly, then quickly fades as fuel runs out.
Webb is showing us star formation pushed to extreme, almost chaotic limits.
Early cosmic conditions may have allowed growth we can't replicate today. These galaxies challenge our understanding of how stars truly form.
They force us to rethink the earliest chapters of cosmic history.
After decades in astrophysics, discoveries like these still surprise me.
The early universe was far wilder than textbooks ever suggested.
Webb reveals a cosmos filled with explosive creativity. And many of these early galaxies defy every rule we built. Each discovery pushes the boundary of what we believe is possible.
We may be witnessing processes that no longer occur today.
Or perhaps our physics is simply incomplete.
These starbursts hint at a universe evolving faster than expected.
The cosmos may have used shortcuts we have never imagined. Starburst events reveal how violent early growth could be.
And why some galaxies matured far earlier than models predict.
Each observation adds another piece to a cosmic puzzle.
We're learning that the universe didn't grow politely or slowly.
It grew through bursts of unimaginable intensity.
And those bursts shaped everything we see today.
These early star factories are storytellers of the universe's youth.
They remind us the cosmos was once young, hot, and unbelievably active. And each new Webb discovery reveals how little we truly know.
The early universe still hides secrets in its brightest moments.
And we're only beginning to understand the forces at work back then.
Every new observation opens another door into cosmic history. These extreme starbursts may be the key to rewriting that story.
And they challenge us to rethink the limits of star formation.
The universe never followed the rules we expected. And Webb is showing us just how wild the early cosmos truly was.
Imagine opening a family album, expecting baby photos on the first page.
Instead of an infant,
you find a fully grown person staring back. That shock resembles what astronomers feel looking at early galaxies.
Some of the earliest galaxies appear chemically mature far too soon.
Heavy elements like oxygen or iron shouldn't exist that early.
After the Big Bang, the universe held mostly hydrogen and helium.
The first stars formed from this simple cosmic mixture.
These first stars lived fast and ended in violent explosions.
Only after these deaths do heavy elements get created and spread. So early galaxies should look chemically young and unevolved.
It's like meeting a 3-year-old who speaks with adult precision.
Such metal abundance means several star generations lived and died quickly.
Imagine a city building and demolishing towers in just months.
Pace feels almost impossible on cosmic timescales.
One theory suggests early stars were far larger and shorter-lived.
These giants could produce metals at hyper-accelerated rates.
Another idea is that early galaxies were extremely dense.
Dense environments make star cycles overlap rapidly.
Think of a forest regenerating immediately after shedding leaves.
The early universe may have worked in a similar accelerated rhythm.
But even with these explanations, enrichment still happened too fast.
Something big may be missing from our picture of cosmic history.
Maybe some galaxies formed earlier than we assume.
Or gravitational lensing could be tricking our measurements.
Or perhaps early cosmic physics operated differently altogether.
Heavy elements change everything about how galaxies evolve. Metal-rich clouds cool quickly and condense into bright star clusters.
They influence how fast gas cools and stars form.
They can accelerate or delay entire galactic life cycles.
Some ancient galaxies may have matured chemically in mere millions of years.
That speed was once thought impossible.
It's like a seed sprouting, growing, and producing more seeds in one season.
Webb keeps reminding us the early universe was shockingly dynamic.
These metal-rich systems challenge our oldest assumptions.
They make us rethink how quickly cosmic chemistry evolved. After decades, discoveries like these still surprise me deeply.
We thought we understood the universe's first chapters.
But these galaxies reveal a story far more turbulent and compressed.
They show us a young cosmos,
racing ahead of our expectations.
And they force us to revisit our assumptions about early cosmic time.
The universe often hides complexity inside its earliest pages. Heavy elements appearing too early hint at deeper mysteries.
They raise the question, what else happened sooner than we thought?
These galaxies challenge us to expand our models of evolution.
And they remind us, the universe rarely follows our rules.
Webb is revealing a cosmos growing faster than our theories allow.
Every new observation opens another door into the unknown.
And these early heavy elements may be a key to that deeper story.
And we've only begun to uncover what happened in those ancient moments.
Imagine watching century-old footage of your hometown and sensing something feels strangely different.
Buildings sit closer, streets look narrower, and the rhythm feels unfamiliar.
That uncanny feeling mirrors what astronomers experience with early universe data. Webb reveals dark matter behaving in ways we never predicted. In today's universe, dark matter forms a delicate, sprawling web. Gravity shapes galaxies along this invisible skeleton. But early dark matter appears denser, sharper, and oddly concentrated.
It's almost as if dark matter once had a different personality. This is strange, because dark matter shouldn't evolve its behavior.
We only detect dark matter through its gravitational influence. For decades, we assumed it was slow-moving and quiet. But Webb's observations show early dark matter pulling much harder.
Early galaxies collapsed faster than any model ever anticipated.
It's like expecting soft sand and stepping onto solid concrete.
So what could explain this unusual concentration? Imagine weather patterns forming faster and tighter than normal.
Dark matter may have created similar gravitational storms.
One idea is that early dark matter interacted more than it does today.
Perhaps it collided or exchanged energy in subtle, unknown ways.
This would make it clump faster and more efficiently.
Another idea is early dark matter was warmer and moved differently.
As the universe expanded, its behavior may have shifted.
Or perhaps cosmic expansion in the beginning worked differently.
All these ideas point to a deeper truth. Something doesn't add up.
And dark matter's odd behavior had major consequences.
Stronger gravity means gas collapses faster into stars.
Galaxies grew earlier and more efficiently than expected.
Webb keeps finding galaxies that look too mature for their age.
Dark matter may be the hidden reason behind their rapid growth.
Think of building on solid ground instead of soft soil.
A stronger foundation means faster construction everywhere.
The early universe, my Mehatid.
And that changed the timeline of cosmic structure formation.
After decades in astrophysics, surprises like this still amaze me.
We thought dark matter's behavior was constant over time.
Webb suggests it may have evolved, just like everything else.
The universe loves breaking the rules we set for it.
And dark matter might be one of its greatest tricksters.
If early dark matter behaved differently, our models must adapt.
We may need to reread the first chapters of cosmic history.
These discoveries hint at deeper forces we haven't uncovered.
Perhaps the universe once used shortcuts in forming structure. Or maybe dark matter hides more secrets than we imagined.
The early cosmos behaved boldly, not quietly.
Its foundations were stronger, stranger, and more dynamic.
And those foundations shaped everything we see today. Webb lets us watch the universe before it settled down.
It reveals a time when gravity acted with unusual strength.
And dark matter gathered itself with surprising determination.
Each discovery pushes us closer to understanding its true nature.
And every answer sparks 10 new questions about the early universe.
One truth remains clear. Dark matter shaped the cosmos profoundly. And we're only beginning to uncover how wild its early behavior was.
The sketch was supposed to be the beginning, the first outline, but suddenly it looked too complete.
The early universe gives us that same uncandle feeling. These aren't full galaxies, yet they're far more organized than clouds.
Webb keeps finding structures that seem ahead of schedule.
Our models say early matter should be loose and disordered.
Instead, we see frameworks forming surprisingly early.
It's as if the universe started construction long before we expected.
These proto-structures act like the first skeletal outlines of galaxies.
And they show up hundreds of millions of years too soon.
It challenges everything we thought we knew about timing.
Think of visiting a sunrise construction site, already half finished.
That same jump happens in the universe's earliest chapters. Gravity may have worked faster in certain regions. Dark matter could have formed early scaffolding. Those scaffolds let galaxies begin forming ahead of plan. Some regions may have had unusually fertile conditions. Matter gathered like seeds dropped in rich soil.
Or perhaps our galaxy formation model is still incomplete.
Webb often reveals physics we didn't account for.
These first drafts of galaxies blur the boundaries we rely on.
They aren't random, but they're not finished either. They are the universe's earliest attempts at building structure.
Each discovery forces us to rethink cosmic timelines.
These proto-structures show gravity practicing its craft. They reveal how matter learned to organize itself.
Before galaxies existed, their outlines were already appearing.
Webb captures these outlines with astonishing clarity.
Earlier telescopes could only see galaxies after they formed.
Webb lets us watch them being assembled. These early structures shouldn't be so dense or organized.
Yet they keep appearing, again and again.
Something accelerated cosmic growth in these regions. Maybe dark matter collapsed faster than theory predicts. Maybe early space had uneven pockets of extreme density.
Or maybe the early universe followed rules we haven't learned.
Whatever the cause, these early drafts are undeniable.
They are too organized to ignore and too early to explain. They may rewrite the first chapters of cosmic evolution.
For me, these findings are the most exciting kind of uncertainty.
They remind us the universe rarely follows our timelines. Nature moves at its own pace, often faster than theory.
Proto-structures reveal the universe learning to build.
And it was learning much earlier than we believed.
These early outlines shaped everything that came after.
They set the stage for stars, planets, and future complexity.
Webb has opened a window into the universe's blueprint phase.
These blueprints challenge our understanding of creation.
They show a universe far more ambitious than our models suggest.
The cosmos wasn't waiting for permission to start building. It began assembling galaxies with surprising confidence. And it did so earlier than any theory allowed.
Imagine standing in a fog field where everything shifts as you move.
That subtle shift mirrors how the universe behaves at vast scales.
We once believed space expanded perfectly, evenly. But Webble's measurements hint the expansion may vary by direction.
Some regions appear to rush outward faster than expected.
Others seem to drift more slowly, breaking our symmetry.
These differences are too large to dismiss as random noise.
Imagine a heat map of the ocean, currents shifting in complex flows.
The universe may have similar invisible currents shaping expansion.
One idea is that large-scale structure drives uneven growth.
Dark matter may create gravitational landscapes that alter expansion.
Some call these motions bulk flows, cosmic drifts of entire clusters.
It doesn't mean the universe has a preferred direction.
It means local conditions may matter more than we assumed.
Picture a loaf rising in the oven, uneven in different areas.
Space may be rising the same way, shaped by its contents.
Another bold idea is that dark energy itself may vary. If dark energy isn't uniform, expansion could change locally.
Traditionally, we picture dark energy as smooth and constant.
But Webb hints it might be dynamic and uneven.
It might even interact with dark matter in ways we don't yet understand.
If so, our cosmology model will need important updates. These inconsistencies don't break the model, they refine it.
Before Webb, many of these signals were simply too faint.
Now, even subtle cosmic breezes leave visible traces.
Some regions may be accelerating because of hidden mass.
Others might be slowed by dense structures we haven't mapped.
Expansion itself becomes a kind of cosmic weather pattern. These flows challenge the idea of a perfectly uniform cosmos.
They suggest the universe follows rhythms we never predicted.
Some regions drift together, as if pushed by distant forces.
Others slow down, as if resisting unseen pressure.
Models assumed expansion was smooth, but the data disagrees.
These variations might point toward new physics.
They could reveal how dark matter shaped early expansion.
They might show dark energy evolving over cosmic time.
Or they may expose hidden structures far beyond our view.
After decades studying cosmology, surprises like this still excite me.
Each anomaly invites us to revisit our deepest assumptions.
The universe has never been obligated to behave simply.
And its expansion may be more alive than we imagined. These flows may reshape how we understand cosmic evolution. They might help explain disagreements in current measurements. Perhaps one region's expansion differs from another's.
Or maybe we're observing early clues to new fundamental forces.
The cosmos still carries patterns we're only starting to hear.
And Webb is giving us the sensitivity to detect them.
One truth is clear. Expansion has more nuance than we expected.
The universe grows unevenly, shaped by forces still hidden. These flows may be subtle, but their impact is enormous.
And they remind us how much more we have to learn. Imagine the young universe weaving structures faster than anyone expected.
Early filaments formed like cosmic highways, stretching across darkness. Gravity shaped the first patterns long before galaxies fully emerged. The cosmic web appeared sooner than our models ever allowed. Matter gathered quickly, forming threads across the infant cosmos. Dense regions pulled material into long, interconnected filaments.
These early structures challenge our timeline of cosmic growth.
Webb reveals a universe organizing itself with surprising speed.
Dark matter sculpted vast networks earlier than predicted.
Filaments formed like bridges linking newborn galaxies. Imagine the young universe weaving structures faster than anyone expected.
Early filaments formed like cosmic highways, stretching across darkness.
Gravity shaped the first patterns long before galaxies fully emerged.
The cosmic web appeared sooner than our models ever allowed.
Matter gathered quickly, forming threads across the infant cosmos.
Dense regions pulled material into long, interconnected filaments. These early structures challenge our timeline of cosmic growth.
Webb reveals a universe organizing itself with surprising speed.
Dark matter sculpted vast networks earlier than predicted.
Filaments formed like bridges linking newborn galaxies.
Imagine the young universe weaving structures faster than anyone expected.
Early filaments formed like cosmic highways,
stretching across darkness.
Gravity shaped the first patterns long before galaxies fully emerged.
The cosmic web appeared sooner than our models ever allowed.
Matter gathered quickly, forming threads across the infant cosmos.
Dense regions pulled material into long, interconnected filaments.
These early structures challenge our timeline of cosmic growth.
Webb reveals a universe organizing itself with surprising speed.
Dark matter sculpted vast networks earlier than predicted. Elements formed like bridges linking newborn galaxies.
Imagine the young universe weaving structures faster than anyone expected.
Early filaments formed like cosmic highways, stretching across darkness.
Gravity shaped the first patterns long before galaxies fully emerged.
The cosmic web appeared sooner than our models ever allowed.
Matter gathered quickly, forming threads across the infant cosmos.
Dense regions pulled material into long, interconnected filaments.
These early structures challenge our timeline of cosmic growth.
Webb reveals a universe organizing itself with surprising speed.
Dark matter sculpted vast networks earlier than predicted.
Filaments formed like bridges linking newborn galaxies.
Early filaments formed like cosmic highways, stretching across darkness.
Gravity shaped the first patterns long before galaxies fully emerged.
The cosmic web appeared sooner than our models ever allowed.
Matter gathered quickly, forming threads across the infant cosmos.
Dense regions pulled material into long, interconnected filaments.
These early structures challenge our timeline of cosmic growth.
Webb reveals a universe organizing itself with surprising speed. Dark matter sculpted vast networks earlier than predicted. Filaments formed like bridges linking newborn galaxies. Early filaments formed like cosmic highways stretching across darkness. Gravity shaped the first patterns long before galaxies fully emerged. The cosmic web appeared sooner than our models ever allowed.
Matter gathered quickly, forming threads across the infant cosmos. Dense regions pulled material into long, interconnected filaments.
These early structures challenge our timeline of cosmic growth.
Webb reveals a universe organizing itself with surprising speed.
Dark matter sculpted vast networks earlier than predicted. Elements formed like bridges linking newborn galaxies.
Imagine the young universe weaving structures faster than anyone expected.
Early filaments formed like cosmic highways, stretching across darkness.
Gravity shaped the first patterns long before galaxies fully emerged.
The cosmic web appeared sooner than our models ever allowed.
Matter gathered quickly, forming threads across the infant cosmos. Dense regions pulled material into long, interconnected filaments.
These early structures challenge our timeline of cosmic growth.
Webb reveals a universe organizing itself with surprising speed.
Dark matter sculpted vast networks earlier than predicted.
Filaments formed like bridges linking newborn galaxies.
Imagine the young universe weaving structures faster than anyone expected.
Early filaments formed like cosmic highways, stretching across darkness. Gravity shaped the first patterns long before galaxies fully emerged.
The cosmic web appeared sooner than our models ever allowed.
Matter gathered quickly, forming threads across the infant cosmos.
Dense regions pulled material into long, interconnected filaments. In the early universe, some galaxies spun in ways we never expected.
Their rotation curves refused to follow familiar rules of motion.
These distant systems moved as if shaped by unseen forces.
Webb revealed galaxies keeping speed, even at their outer edges.
Some young galaxies rotated like mature giants, far beyond their age.
Their mass distribution defied the equations we rely on.
The math struggles to explain how these galaxies hold together.
It's as if gravity behaved differently in the young cosmos. Dark matter may have clustered in unusual early patterns.
Chaotic cosmic flows could have shaped their strange motion.
In the early universe, some galaxies spun in ways we never expected.
Their rotation curves refused to follow familiar rules of motion.
These distant systems moved as if shaped by unseen forces. Webb revealed galaxies keeping speed even at their outer edges.
Some young galaxies rotated like mature giants, far beyond their age.
Their mass distribution defied the equations we rely on.
The math struggles to explain how these galaxies hold together.
It's as if gravity behaved differently in the young cosmos.
Dark matter may have clustered in unusual early patterns.
Chaotic cosmic flows could have shaped their strange motion.
In the early universe, Some galaxies spun in ways we never expected.
Their rotation curves refuse to follow familiar rules of motion.
These distant systems moved, as if shaped by unseen forces.
Webb revealed galaxies keeping speed even at their outer edges.
Some young galaxies rotated like mature giants far beyond their age.
Their mass distribution defied the equations we rely on.
The math struggles to explain how these galaxies hold together.
It's as if gravity behaved differently in the young cosmos.
Dark matter may have clustered in unusual early patterns.
Chaotic cosmic flows could have shaped their strange motion.
In the early universe, some galaxies spun in ways we never expected.
Their rotation curves refuse to follow familiar rules of motion.
These distant systems moved, as if shaped by unseen forces.
Webb revealed galaxies keeping speed even at their outer edges.
Some young galaxies rotated like mature giants far beyond their age.
Their mass distribution defied the equations we rely on.
The math struggles to explain how these galaxies hold together.
It's as if gravity behaved differently in the young cosmos.
Dark matter may have clustered in unusual early patterns.
Chaotic cosmic flows could have shaped their strange motion.
In the early universe, some galaxies spun in ways we never expected.
Their rotation curves refuse to follow familiar rules of motion.
These distant systems moved, as if shaped by unseen forces.
Webb revealed galaxies keeping speed even at their outer edges.
Some young galaxies rotated like mature giants far beyond their age.
Their mass distribution defied the equations we rely on.
The math struggles to explain how these galaxies hold together.
It's as if gravity behaved differently in the young cosmos. Dark matter may have clustered in unusual early patterns.
Chaotic cosmic flows could have shaped their strange motion.
In the early universe, some galaxies spun in ways we never expected.
Their rotation curves refuse to follow familiar rules of motion. These distant systems moved, as if shaped by unseen forces.
Webb revealed galaxies keeping speed even at their outer edges.
Some young galaxies rotated like mature giants far beyond their age.
Their mass distribution defied the equations we rely on. The math struggles to explain how these galaxies hold together.
It's as if gravity behaved differently in the young cosmos. Dark matter may have clustered in unusual early patterns. Chaotic cosmic flows could have shaped their strange motion. In the early universe, some galaxies spun in ways we never expected. Their rotation curves refused to follow familiar rules of motion. These distant systems moved as if shaped by unseen forces.
Webb revealed galaxies keeping speed even at their outer edges.
Some young galaxies rotated like mature giants far beyond their age.
Their mass distribution defied the equations we rely on.
The math struggles to explain how these galaxies hold together.
It's as if gravity behaved differently in the young cosmos. Dark matter may have clustered in unusual early patterns.
Chaotic cosmic flows could have shaped their strange motion.
In the early universe, some galaxies spun in ways we never expected.
Their rotation curves refused to follow familiar rules of motion.
These distant systems moved as if shaped by unseen forces.
Webb revealed galaxies keeping speed even at their outer edges.
Some young galaxies rotated like mature giants far beyond their age. Their mass distribution defied the equations we rely on. The early universe formed stars faster than any model predicted.
Webb reveals galaxies that lived multiple star cycles shockingly fast.
These young systems show heavy elements far earlier than expected.
It's as if the cosmos had a hidden fast-forward mode.
Dense early gas clouds collapsed into stars at incredible speed.
Massive first stars lived fast and ended in explosive bursts.
Recycling cosmic material happened in rapid, compressed cycles.
Star birth and death unfolded much quicker than classical timelines. Chaotic collisions triggered intense waves of star formation.
The young universe built chemical complexity far too early. The early universe formed stars faster than any model predicted.
Webb reveals galaxies that lived multiple star cycles shockingly fast.
These young systems show heavy elements far earlier than expected.
It's as if the cosmos had a hidden fast-forward mode. Dense early gas clouds collapsed into stars at incredible speed.
Massive first stars lived fast and ended in explosive bursts.
Recycling cosmic material happened in rapid, compressed cycles.
Star birth and death unfolded much quicker than classical timelines. Chaotic collisions triggered intense waves of star formation.
The young universe built chemical complexity far too early. The early universe formed stars faster than any model predicted.
These young systems show heavy elements far earlier than expected.
It's as if the cosmos had a hidden fast-forward mode.
Dense early gas clouds collapsed into stars at incredible speed.
Massive first stars lived fast and ended in explosive bursts.
Recycling cosmic material happened in rapid, compressed cycles.
Starbirth and death unfolded much quicker than classical timelines.
Chaotic collisions triggered intense waves of star formation.
The young universe built chemical complexity far too early.
The early universe formed stars faster than any model predicted.
Webb reveals galaxies that lived multiple star cycles, shockingly fast.
These young systems show heavy elements far earlier than expected.
It's as if the cosmos had a hidden fast-forward mode.
Dense early gas clouds collapsed into stars at incredible speed. Massive first stars lived fast and ended in explosive bursts.
Recycling cosmic material happened in rapid, compressed cycles.
Starbirth and death unfolded much quicker than classical timelines.
Chaotic collisions triggered intense waves of star formation.
The young universe built chemical complexity far too early.
The early universe formed stars faster than any model predicted. Webb reveals galaxies that lived multiple star cycles, shockingly fast. It's as if the cosmos had a hidden fast-forward mode. Dense early gas clouds collapsed into stars at incredible speed.
Massive first stars lived fast and ended in explosive bursts.
Recycling cosmic material happened in rapid, compressed cycles.
Starbirth and death unfolded much quicker than classical timelines.
Chaotic collisions triggered intense waves of star formation.
The young universe built chemical complexity far too early.
The early universe formed stars faster than any model predicted.
Webb reveals galaxies that lived multiple star cycles shockingly fast.
These young systems show heavy elements far earlier than expected.
It's as if the cosmos had a hidden fast-forward mode. Dense early gas clouds collapsed into stars at incredible speed.
Massive first stars lived fast and ended in explosive bursts.
Recycling cosmic material happened in rapid, compressed cycles.
Star birth and death unfolded much quicker than classical timelines. Chaotic collisions triggered intense waves of star formation.
The young universe built chemical complexity far too early.
The early universe formed stars faster than any model predicted. Webb reveals galaxies that lived multiple star cycles shockingly fast.
These young systems show heavy elements far earlier than expected.
It's as if the cosmos had a hidden fast-forward mode.
Dense early gas clouds collapsed into stars at incredible speed.
Massive first stars lived fast and ended in explosive bursts.
Recycling cosmic material happened in rapid, compressed cycles.
Star birth and death unfolded much quicker than classical timelines.
Chaotic collisions triggered intense waves of star formation.
The young universe built chemical complexity far too early.
The early universe formed stars faster than any model predicted.
Webb reveals galaxies that lived multiple star cycles shockingly fast.
These young systems show heavy elements far earlier than expected.
It's as if the cosmos had a hidden fast-forward mode. Dense early gas clouds collapsed into stars at incredible speed.
Massive first stars lived fast and ended in explosive bursts.